In this session, we will discuss the equations of motion. Now, I'm sure you've already studied these equations of motion. So let me first start by highlighting the key things about these equations. So the first important thing that you must remember is that these equations are vector equations. That is, all the variables involved are vectors and they must therefore be substituted with suitable signs. The second important thing to remember is that these equations are one-dimensional equations. So, you must choose a particular dimension and then apply these equations for that dimension. So, you've already seen these equations being applied in the case of one-dimensional motion. We will later see that when we have two or three-dimensional motion, we basically have three separate equations for each dimension. Right. And the third and the most important assumption, the key feature here, is that we are working under the assumption that acceleration is constant. So these equations are valid if and only if the acceleration is constant. Right. So let's now derive these equations. Let's start with the very assumption that we have made, that acceleration is constant. Now, we have so far seen that acceleration of an object is defined as a rate of change of its velocity. So what we basically have is that dv by dt is equal to constant. Right. So now you know how to handle such basic differential equations. So we take dt to the other side. You have dv is equal to c into dt. Integrate both sides. While we do this, we let time vary from 0 to t, and correspondingly on the left hand side, when t is 0, the velocity will obviously be the initial velocity, because that is how we define initial velocity. It is the velocity at the start of an interval, and the final limit is t, and the velocity at that point, which is the velocity at the end of the interval, which is basically the final velocity. So, the left hand side, when you integrate dv, you'll have v, in which you'll substitute these values. So, your left hand side becomes v minus u. This is equal to c is a constant. You can take that out of the integral, and integral dt from 0 to t, I'm sure you know, will be equal to c into t. Right. Now the other thing that you must notice here is that the constant that we are talking about is nothing but the acceleration itself. So I can substitute that here and I get v minus u is equal to a into t. So this is the first equation of motion. Now, as I said, that these equations are basically applicable only in one dimension. So what we can do is, we need not write these arrows because they are one-dimensional vectors. And in one-dimensional vectors, we had discussed that sign is enough to indicate direction. So this is why most of the time you would see the equations are simply written as, the first equation would be written as v is equal to u plus at. But make no mistake, these are not scalar quantities, these are vector quantities. So you must substitute velocity and not speed. Right. Next, further, this velocity can be written as a rate of change of distance. So I could say that ds by dt, where s symbolizes displacement, so ds by dt is equal to u plus at. Now once again, I'm not putting vector sign on s, but remember, this is displacement and not distance, and hence this is a vector quantity. So once again, take dt to the right hand side. You have ds is equal to u plus at dt. Once again, we can integrate both sides. On the right hand side, we'll let the limits go from 0 to t, and on the left hand side, the limits would be 0 to the final displacement s. Right. So on the left hand side, it is fairly easy. The integral simply leads you with an s, which is the displacement. On the right hand side, you know, whenever you have sum inside an integral, you can write it as the sum of integrals. That is, you can write this as u dt plus at dt. Now when you're integrating u is a constant, and hence let me do it. So what you have is u dt from 0 to t plus at times dt, once again 0 to t. U being the constant would come out of the integral. Integral of 1 is t, so the first term becomes ut. For the second term, acceleration is a constant because that is the assumption we are working under, and t dt would give you t square by 2. So the second term becomes at square by 2, and hence you have s as ut plus at square by 2. And you know that this is the second equation of motion. For the third equation, let's come back to the fact that v is equal to ds by dt. Right. Now what we are going to do is we are going to multiply the right hand side with the term dv by dv. So you can see that dv by dv is 1, and hence I can do that. Now I'm going to rearrange these terms and write it as ds by dv into dv by dt. Now dv by dt, you know, is nothing but the acceleration. So you could say that v is equal to a into ds by dv. Right. In the current form, I'm sure you can see what is to be done next. You will bring dv to the left hand side. So we get v dv is equal to a ds. Once again, integrate this equation. Let s vary from 0 to s, and v, once again, we have the start and the end of an interval, so it will vary from the initial velocity to the final velocity. Right. So v dv when integrated will give you v square by 2, and on substituting limits you will be left with v square minus u square by 2, and on the right hand side a is a constant, hence it comes out of the integral. You integrate ds, you're left with s, so the right hand side is simply as. So when you rearrange this, you get your final equation, which is the third equation of motion, that v square minus u square is equal to 2as. So here we have the three equations of motion. In addition to these, you would often see another equation, which is the equation that gives you the distance covered in the nth second. Now, if you look at the second equation, the second equation gives you the displacement in time t, that is the duration or the interval of t seconds. But what if we want to find the distance covered in a specific second? For example, if you were to find the distance covered from t equal to 0 to t equal to 5, you could use this equation. You could substitute t as 5, and this equation would give you the displacement in the 5 seconds. But what if you wish to find the displacement in the 4th second, in that single 4th second? So how will we do that? Let's look at it in the next slide.